Okay, now, what we're doing today is we are reviewing and doing more material today and tomorrow. So, let's begin right away without any further discussion. Is that clear? Roanoke, you with me?
All right, of course.
Of course, okay. I'm sorry, I forgot that. Okay, so we have this set of vocabulary that you should know. What's a proton? Anybody know? Proton is where?
Positively charged.
It's positively charged. It's in the nucleus. It has a mass of 1 gram, 1 pound, 1 kilogram, 1 what? Anybody? 1 atomic mass unit. What is one atomic mass unit? What is 1 atomic mass unit? What's it based on? A gram is 1,000th of a kilogram, which is a construct by man. What is it?
It's the weight of the protons plus the neutron of that.
No, a neutron has a mass of 1 atomic mass unit as well. But do you remember where, have we got over the greeting and the felicitations and the good mornings? Excellent. I like that. Very friendly guy. When I hear the word Roanoke, I think of friendly, okay? Excellent. Okay. It is based on 1/12 the mass. You're snapping your fingers. So in other words, you want to keep a low profile. Hopefully I don't hear you. So you snap your fingers. That's a great style. I'll tell you. You should go into the spy business. Excellent. Excellent. I didn't hear that at all. Okay. So it's 1/12 of a carbon atom. The carbon atom has an atomic mass of 12. So 1/12 would be the mass of 1 particle. It has, a carbon atom has 6 protons plus 6 neutrons. Clear? So 1/12 of that would be the mass of a proton, and a neutron is the same mass. Clear? So a proton is 1 atomic mass unit, which is 1/12 that of a carbon atom by standard. That's the standard. Now, excuse me, I had some markers. So, we know what the atom is. The neutron is a neutral portion of the what? Where's the neutron? It's outside?
No, it's inside
Really?
that.
It's inside the nucleus, right? But you knew that, right? You were just testing me. Excellent, excellent. Okay, you have an electron. The mass number is what? What's the mass number?
Number of protons.
The number of, how do we say it? How do we say it? How do we say it? I'm going on your reading plus your past experience. How do we say it? It's total number. Here's another vocabulary word for you. Nucleons. The total number of nucleons. What do you think that would mean? Romina, what does that mean to you? Total number of nucleons. What would that mean to you? Nucleons. What is it? Total number of members of the nucleus, maybe? See, it's not spelled like neutron, it's spelled like nucleus, the beginning of nucleus, right? So it would be, the mass number is the total number of what? Protons and neutrons in the nucleus, correct? Okay, good. Atomic mass unit we've done. What's an isotope? Do you remember? You're going to have to write this one down, guys, because nobody gets this. It sounds like, well, I was born in 1955, so I watched a lot of 1950 science fiction movies on television in the 60s. So when I hear the word isotope, I hear this, I think of some science fiction movie, the word isotope. But an isotope is what? Say that again. I like that, but say it again.
The number of protons are the same, but the number of mass is different.
Good, I like that. Very, very good. May I put it a little differently? I'll tell you what she said. It's an element where, two elements, where the number of protons are the same, right? So it's the same element, and the number of neutrons are different, so the atomic mass is different. And that's good, I like that, okay? For instance, here is, and we're going to use these numbers in a minute. There are 3 isotopes of hydrogen: protium, deuterium, and tritium. These are naturally occurring, and this is artificial. This is man-made, okay? So this is how, and we're going to go over this. This is how you write a chemical symbol. You have a superscript and a subscript, yeah? The superscript is the mass number. The superscript is the mass number, the number of protons and neutrons. And the subscript is the number of protons, the charge, but we really consider it to be the atomic number. But it's really the number of protons, really. So we don't say +1, but it really is. You know, it's never +1. The only time you see signs in the subscript where you know it's a charge is when you talk about, when you look at a proton. A proton is, the subscript is +1 and the superscript is just 1. So the mass is 1 and the charge is +1. For a neutron, the charge is 0 and the mass is 1. For an electron, the charge is -1 and the mass is 0. The mass isn't 0, but we take it as 0 because of something called significant figures, because it's about 1,000th, some 1,000th of the mass of a proton. So when you do calculations, it doesn't really matter. It doesn't matter, you know, unless you're, it just doesn't matter. Unless you're going out as a lot of significant figures, it doesn't matter. Okay, and it, you know, that's not particularly satisfying because you're not sure what significant figures are yet, but you will, and it'll make more sense. But it's just they're not necessary. Okay, so a period is what? What's a period? As he's going like something, okay, do something like this, okay. You've got the idea. Period is the horizontal row in the periodic table, okay. First period is hydrogen and helium. Second period is lithium, beryllium, boron, etc., right? Yeah. And family, or what? What's family? Family is the groups, or the vertical columns, the families. You have the oxygen family, the halogen family, the alkali family, right? That's all on your test. What's the alkali family? We have 18 columns, right? We have 18 columns, right? What's the alkali family? Anybody? Group 1, excellent. Group 1, excellent. What's the alkali earth family? Group 2. Well done, Samuel. Well done. Group 2. What is the chalcogen family? Not in your book, but an old term. Chalcogens. Chalcogens is the oxygen family. We call them chalcogens. What's the halogens? 17. Well done. 17. What's the noble gases? What column is that? 18. Good. What are the transition elements? In between 2 and 13. Well done. Well done. So if you look at your periodic table, it goes from scandium, which is next to what? What's scandium next to? Scandium is next to what? Calcium. Okay. So if you think down, try to visualize. You have hydrogen, lithium, sodium, potassium. Next to potassium you have calcium, and then next to calcium you have scandium. Okay. That middle chunk. 1, 2, 3 times 10. It's like 30 elements. They're called the transition elements. What are some characteristics of the transition elements? Starts with an M. Malleable metals. Malleable metals. Yes. what transition metal is not malleable at room temperature?
100.
Well, it's a clear-cut one. I mean, there may be others, but clear-cut.
Is not?
Mercury. Mercury is a liquid at room temperature, right? Where are the inner transition elements? Remember,
Yeah.
you asked me
In the bottom.
what those bottom elements were, and I kind of separated it out, and I made 32 columns, and you had the first 2 columns, then you had 14 columns, then you had the 10 of the transition elements. So where are the inner transition elements? And that's,
In the bottom.
yeah, there are the 2 rows at the bottom that actually came out of the base of the table, and they're put at the bottom. It just makes the table more what? More compact, more readable. Okay, good. What else? All right, that's all for that. Okay. Where are metalloids? Metalloids. 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 Where? Between metals and non-metals. Okay. There's like a little line that goes down between them.
Yeah,
Right.
zigzag line.
Zigzag line that goes from upper left to lower right, right? And where are the metals?
Left side.
Non-metals are on the left side. Okay, good. Anything else on that? Is that good? Yeah. Okay. So those are the vocabulary words. So I just needed to review that as a basis for some of this other stuff.
Just don't erase.
Yes. Don't erase it. You want to copy it? It's on the tape, dude. I mean, yeah. Okay. All right. Let's look at this chart. This mass number, I think, goes here. All right. Sodium. Let's fill out this column, these rows. Sodium. What's the atomic number of sodium? Do you remember? You should have memorized it. Hard to use. It's hard to use the M word, you know. I can't use that word in mixed company. You know, it's a very vulgar word. What is it? 11. Excellent. 11 is the atomic number. This is wrong. Sorry. What is the mass number? 23. What's the number of electrons? These are all ground state. Yeah, what's the number of electrons? What is it? 11. Good. Excellent. You guys are good. What's the number of protons? 11. What's the symbol with the superscript and the subscript? It's Na, right? And what's the superscript? The mass number, right? Which is here. And the bottom number is the atomic number? 11. Good. Well done. You get it? Easy? Okay. You're going to have one just like this. Do it now. Uranium. You're going to have to look this up. You know, get out an electronic device. You're going to have to look that up. All right, let's do one that's easier. You look that up. Can you look that up for us? Let's do sulfur. Sulfur's pretty easy, actually. What's sulfur?
Sir, I got uranium.
You got uranium? Okay, good. What is the mass number of uranium? In other words, just round it to the nearest whole number.
238.02.
I said round to the nearest whole number.
238.
238. Excellent. Right? Right? And you refine it. What's the bomb capable isotope? 235. So you have to separate it out with a tweezer. Okay. So what would the number of electrons be? 92. What would the number of protons be? 92. What would the number of neutrons be?
238 minus 92.
Do it.
146.
Do it. 238 minus 92. Come on, guys.
146.
What is it?
146.
146. What's the symbol?
U.
238
and 92.
Over what? I'm making a big alley too here, sorry. 238 over 92. Excellent. Okay, good. What's arsenic? Arsenic.
Where is arsenic, sir?
Arsenic. You need to know arsenic. I may have put that in. Sorry. You're going to have to add that to your treasure trove of things. You need to know arsenic, AS. Arsenic, AS. Lower middle right.
75.
75 is what? The atomic number?
No, mass number.
That's the mass number? 75? Oh, I have 75, okay. And what's the atomic number?
33.
What is it?
33.
33. Okay, and what is the number of neutrons?
52. Oh, sorry, 42.
Okay, and what is the number of electrons?
33.
What is the atomic number?
33.
And what is the symbol?
AS 75. 33.
All right, sulfur. Shall I do the atomic mass for you?
33. Sorry, 32.
Then what? This is easy. 16, 16, 16, and then S, 32, 16. Easy? Right? Pretty easy, huh? It's like a giveaway. And what about titanium? That's next to scandium, I think. It's like 22? Oh gosh, it is 22, right.
They're 48.
48? So this is going to be what?
22.
26? This is 22?
Yes, sir.
Then, no, this is wrong. This, I put that in the wrong place, that's 48. And then this is 22. And then what is the symbol?
TI.
Ti, titanium. Those three are actually very important metals. Scandium is 21, titanium is 22, and vanadium is 23, right? Vanadium is 23. Very important industrial applications. Titanium is like steel, but it's very, very light. It's very important in the... What do you need that's very strong but very light? What do you think you need that in? And takes heat very well, by the way. The aircraft industry, titanium. Bikes are made of titanium as well. You have to pedal, trust me, you want to play. All right, are we done?
No, sir, we didn't finish.
We didn't finish?
Titanium symbol, sir.
Oh, yeah. So you got 48 over 22? All right, we're done now, right? I'm going to erase that because of these two problems I want to do next. Okay? Now, when you look at, Al, you have a periodic table there, right? Let's write down a few atomic masses. What's the mass of hydrogen? Okay, everything that's on there, not mass number, atomic mass. What is it?
1.
Something like that?
Okay, yeah, 1.00794.
79, okay. No, not calcium's too easy. Give me, I don't know, titanium.
47.867.
Give me, right? So you can see that, you say to yourself, well, wait a second. The mass number is 22. Sorry, 48, right? The mass number is 1. What are all these decimal places? Right? Well, this is the answer. Listen carefully to my words. The atomic mass is the average atomic mass, the average mass number based on isotopic relative abundances. What does he mean? Well, let's do it this way. I have 3 isotopes of hydrogen. I have protium, deuterium, and tritium. Protium has 1 proton. Deuterium has 1 proton and 1 neutron, give you a total of 2. And then tritium has 1 proton and 2 neutrons, total of 3. Let's say we take a giant collection of hydrogen, just a random sample from nature, okay? And we put it in a tank. And we somehow pick out 1,000 atoms. Now, I'm making up this data. It doesn't really exist. It doesn't exist. But I'm making it up, okay? Just for demonstration purposes only, yeah? What I want to do is, I'm going to pick out 1,000 atoms of hydrogen. I'm going to find its total mass, and then divide by 1,000. Wouldn't that be the average mass? Right? If I wanted to find the average mass of everyone in here, I weigh 100 kilos. Oh, you don't want to tell me. But you would tell me your weight, right? And then I would divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people, right? That would be the average mass, right? And if you gave me your weight in whole numbers, 100 kilograms, whatever, okay, then you would say, then all of a sudden you get a decimal. Well, where did the decimal come from? Well, because you divided it by 13, you're going to get a decimal. Just the way it is, right? Well, the same is true. It's very simple, actually. People say, well, it's based on the average relative abundances of the isotopes. Doesn't that sound like really complicated?
Yeah.
It's actually kind of silly.
What's the meaning of abundance?
Abundance, amount. What's the abundance of the what's the abundance of the people in Dhaka? 15 million? Okay? It's abundance, amount. Okay. So I have 995 proteins. What's the total mass of that in atomic mass units? 995 have a mass of 1. So what's the total mass of that? I have 995 protein atoms. Right? What's the total mass of that 995 atoms? If each one has a mass of 1, and there's 995 of them, then it would be 995, right? I know what you're thinking. You're thinking, oh, it must be a complicated answer because we're talking about average isotopic abundance. But it's really very simple. Isn't that simple? Isn't it? Okay. I have 4 that have a mass of 2. So what's the total mass of that? 8. Good. I have 1 that has a mass of 3. So what's that? 3. Add it up. 13, 6. Is that right? Is that right?
So it's 105.
Right? Divide by, so it's 1,006. Divide by 1,000. What do you get? What's the average mass?
10006.
Easy? I mean, come on. Come on. Come on. Come on. I mean, it's kind of silly, isn't it? All right, let's do another. Shall we do another one quickly? One that's very similar to the one on the test. What happens if I did this? What happens if I said, right, carbon 12 and carbon 13. What did you want me to put this on? Okay. It's carbon 12 and carbon 13. This is 1.1% of all carbon is carbon 13. And this is 89.9%. Okay? So what would be a convenient number of atoms to base this on? I could base it on 5,886 atoms, right? I would just take this amount of that and this amount of that, right? But let's just base it on what? What can we automatically base it on?
1000.
We can wave our hands and do whatever we want. This is math, remember? We control math. Math doesn't control us.
1000.
No. 100, yeah, right? So if I base it on 100, French guy alert.
It's a great time during your lunch time, snacks time, okay? Please you come to my room, just for eating your snacks and good.
Now, if you were going to do it properly, you would say it in French. And if they didn't show up, they would get detention because they didn't understand what you said. Right?
Please come to my room.
No, say it in French, dude. Come on, let's go. Let's hear it. I don't believe you can actually speak French. I've never heard you speak French. I've never heard you speak French.
Alors, les républicains de Gratman, vous venez à mon chambre. Il passait votre femme et le
See whatever he wants to say.
All right, now I'll call the ambulance because his throat just closed up. What did he say? They go to the guy in front of the bathroom canteen? Is that what he said? Yeah. Okay, so if I have 100 atoms, I have 89.9. Excuse me. if I have 100 atoms, 89.9 of them are carbon 12. So I would multiply it by what? 2?
Sorry, 12.
Where'd you get 2? Can I say something really cruel, but very honest? And I mean no disrespect. I'm going to say this on film, but I mean no disrespect. It's kind of ironic. You're kind of tired now, aren't you? But I trust you that you're just tired and a little tired, right? Probably. What time did you go to bed last night? What time did you go to bed last night? 1 o'clock in the morning? 12 o'clock, midnight? So it wouldn't be unusual. I would excuse myself for the class. I'd get somebody in here to cover the class, and I'd go to my supervisor and I'd say, we need a drug test in room 503. Did it 100 times. And they came out positive like 495 times. That's a little bit of exaggeration. Maybe 497, but anyway. So you try to, if you don't feel well, you tell me before class. I don't feel well, I was out partying all night, no, I don't feel well, I've been throwing up. Tell me before class, so I know that you're not being weird, okay? Good idea? Excellent. So, somebody multiply 89.9 times 12.
1078.8.
1078.8. Okay, good. You got that? Okay. Now, then you multiply 1.1 times what?
13.
13.
14.3.
14.3. Now, add them together.
1093.1.
1093.1. Now, something's wrong, dude. Is this right? Did you multiply 89.9 times 12?
Yes, sir, it's 1.
You did. You did? You're sure? All right. This is the data I gave you. Okay. And you multiply 1.1 times 13. That's that. And the answer would be what? This is terrible data, but anyway, that's okay. We're doing it right. So what's the answer? Add these two together.
1093.1.
What is it?
1093.1.
And then what would I divide it by? What would I get? What would I get?
25?
This is from the book, by the way. It's not me.
100 or
I get 10.93, right?
What?
Right? Divided by 100. The number of atoms, right? Wouldn't I get 10.93? Wouldn't I? Yes? Yes? Look, this is not as hard as it looks. I'm a little bit, because it's carbon, so it should be 12 exactly. But why is it wrong? And I'll ask that question in a second. But I'm basing this on 100 atoms, which I can, because I say 100 atoms, I say 89% of the 0.899 of 100 is 89.9, multiplied by 12, right? That's that. And then 1.1 is this, right, 100 atoms, multiplied by 13, I get 14.3, add them together, I get 10.93. Why is it wrong, you think? I don't know why the book did this, but whatever. Because carbon 14 is missing. It's a whole isotope. Carbon 14 is missing. Just bad data.
So you will add the 3 now?
What is it?
You will add the 3 of them now?
Well, no, I don't have the data. In other words, the percentages are definitely wrong. According to that data, listen to me. This is an important discovery in science, and the discovery is this. This is the data you're given. Okay? Now, I'm going to reduce the data. I'm going to do a calculation to see if I'm right. This was the thesis of the experiment. The thesis of the experiment was to, we're a lab group, we're a lab team. Let's say that I gave you data. You said, we have to determine the average atomic mass of carbon, otherwise known as simply the atomic mass of carbon. This is the data I gave you. This is what we get. Correct? What do you have to report? This. You can't say, well, I know it's 12. Let's just say it's 12, because we know it's 12. No, you have to report this, correct? You get it? In a lab setting, you have to report what you get. You can't make stuff up. Clear? Enough? You get it? This is what the book gave us, so we're going to go with that. Is this right? No. But it's probably missing the carbon-14 data. I'm telling you that's where the error probably occurred. Now, let's do the next thing, which I think is kind of fun. It's actually quite amazing. Now, you've heard of black holes? Yes? Describe to me what you know about a black hole.
It's a hole which is black.
The hole which is black. Excellent. Typical high school student simply rephrasing the question in the form of an answer and hoping he's right. Yes?
It's the last stage of the star.
It's the last stage in the life of a star. I like that a lot. Okay, what else? Anybody?
And it's filled with, it has
It's really, it's like sucks every, it's really, what? Heavy, right? It's heavy, 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 heavy. Dense, 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 dense. It just sucks in light, doesn't it? That's why it's black, right? It's black because it absorbs light, right? What does black do? Black absorbs light. Does this black absorb all light?
Yes.
Not really, because we can see it, but we see it a lot through contrast, right? Yes? Put your hand on that table. Oh, can't see it. Oh, yes I can. But the point is that it absorbs all light. Even the light that would be reflected from my hand, it would absorb if it were a black hole. So you wouldn't see your hand. Because the light would hit your hand and then go into the black hole. It wouldn't be reflected off your hand, you see? So you know that it's not pure black, or a black hole, really. All right?
Sir, can humans make?
Excuse me?
Can humans make black holes?
Can humans make black holes? Yes.
I'm gonna sell black holes.
I think we can make black holes. You have to look into that. Why don't you look it
Sir,
up?
black holes absorbs everything that's in here. So if you make a black hole, that will go inside.
Well, I'm going to explain what a black hole is.
Both of them are.
Okay, I'm going to explain what it's made of. You guys finished or feel better? Now that you've disturbed me? Excellent. Hey, I'm here to serve, dude. You know what I mean? I'm here to be disturbed. Okay, good. Well, this is what we're going to do. You ready? Now, the density of Earth is this. Now, let me explain. The density of Earth is approximately 5.5 grams per cubic centimeter. All right? Now, you may think that's a lot, but it's really not. That's the density of rock is like 2 or 3 or 4, right? The density of water is 1. Density of water is 1. Can I have everyone's attention over here? Excellent. This is interesting. Believe it or not, I know. If something's boring, I will tell you. Well, maybe not. I won't say anything about it. But if something's interesting, I'll tell you. This is interesting. It is. The density of iron is approximately 8. Something. Right? It's approximately 8. 7 to 8. All right? We'll put 7 to 8. I don't know what it is. Look up the density of iron.
7.87.
7.0 is pretty good. 7.8. Okay, good. Now, look at the density of rock. See if it gives you anything. Density of rock is really not much more than water. Believe it or not. What is it?
One kind of rock, sir.
What is it?
What kind of rock?
Just say rock.
So it is 2.65 grams.
2.65. All right. Rock. So rock is only 2.5 times the density of water. You'd think rock would be more, right? It's really not. Okay? So this is the density of Earth. Okay? Now, I want to tell you what the density of pure. I feel like I'm like a stand-up comedian in like a bar. like cocktail lounge where everybody's like having conversations and okay, I see. And no one's paying attention to me. I feel like I'm doing, you know what I mean? I feel like I'm doing a stand-up act in a cocktail lounge and no one's paying attention to me. You know what I mean? I'm just standing up here. You guys are having dinner, having conversations, and yeah, exactly. Okay. Yeah, okay, yeah. Listen, this is the density of. This is wrong. What's the density of nuclear material? Look up density of nuclear material. I think it's 17 actually.
Nuclear materials.
Look up density of nuclear material. I know, he has an Android. Huh?
2.3 into 10 to the power 17 kilometers.
2.3 times 10 to the 17?
Yeah.
Is that right? Okay. So this is the density of nuclear material. 2.3 times 10 to the 17th kilograms per cubic meter. Look at part 2 now of this lesson, which is essentially to determine the radius of the Earth if the Earth were pure nuclear material. In other words, what would the radius be of a sphere whose mass was that of the Earth, but was made of pure nuclear material?